So, welcome to today's plenary session. It is a great pleasure to introduce our plenary speaker, Ulrich Pferschy of the University of Graz. So Ulrich is a very active member of our CO community. I have known Ulrich since a long time ago. So in particular, I remember we had a very good interaction at CO 2004 in Lancaster. Okay, so let me just very briefly introduce our speaker. So Ulrich had his PhD in 1995 from Graz University of Technology. He did his postdoc between 1996 to 2001 at the University of Graz, where he has working since then, all the way being promoted to associate professor to full professor. In 2001, Ulrich had a habilitation at the University of Graz. A few years later, in 2013, Ulrich got an Italian habilitation from the Italian Ministry of Education, Universities and Research. And Ulrich also had some admin work, including head of the department of the Operations Information System at the University of Graz. And he also sits on a number of editorial boards, such as European Journal of Operational Research, Mathematical Methods of Operations Research, Journal of Combinatorial Optimization, and Central European Journal of Operations Research. Ulrich also has a huge number of publications, including a book and over 80 journal articles, a number of journal papers still in the pipeline, of course, numerous conference papers. Without further ado, let's give the screen to Ulrich Pferschy. Ulrich, please, screen is yours.
Okay, so thank you both for the nice introduction. And thank you for the organizers for inviting me. I want to talk about an allocation problem, so allocating items to agents in the context of fairness and also conflicts. So the central layout of the whole talk will be fair allocation. So we are always talking about a set of items and let's say n items and k agents. And the items should be given to the agents in some way, probably not all of them. So each agent should receive a subset of the items and they are clearly disjoint. And we want to look at this trade-off between the maximum efficiency. So how is the solution from a global point of view? And what about the fairness if you consider each individual agent? And this will be a guideline through the whole talk, which will consist of 3 parts. I will try to introduce some problems that are probably interesting for some of you, and then go into some depth here and there, which is probably of limited interest for everyone, but for some of you, it's probably also interested to know what are the tools that we use and what is actually done instead of just announcing results. So let me start with the first part, which is about fair allocation under a bounded resource, and it's based on joint work with Gaia Nicosia and Andrea Pferschy. So in this setting, we have a resource, so like some capacity that can be utilized by selecting items, and the items belong to one of 2 sub agents, A or B. And we want to select items and assign them to A and B such that the maximum utility is as large as possible. So let's be a bit more formal. So each item from a set S has a certain value, Wi, and what we want to look for, or not we, but some central decision maker, a subset of items to give to A, another subset to give to B, such that the total utility, so the sum of weights from both subsets, is as large as possible, but still limited since our resource is limited. Now that's of course a simple subset sum problem, very old, well-known stuff. Clearly, such an optimal solution, it's also called utilitarian solution, may be highly unbalanced. So it could be the case that one agent gets almost everything and the other agent gets nothing. And so from a fairness point of view, we want to find a solution or an allocation which still is limited by the overall capacity, but which fulfills some sort of fairness criteria. It's a bit related to fair division, but in fair division, all items have to be partitioned, while we only select a subset of items to give to the two persons. Let me mention that in all this talk, we are always speaking of one central decision maker. So one algorithm, one rule, whatever. We are not talking about multi-agents who are acting on in their own interests. So everything is centrally decided. So we will consider two different settings. One is a setting of shared items. So you have one set of items and you can give an item to A or to B. The other story are separate items. So you have two a priori disjoint subsets, and agent A gets some items of subset SA, and agent B gets some items of subset SP. In both cases, of course, the capacity bound has to hold for the overall sum. So if you consider this toy example, so there are two items for agent A, 1 and 1/2, and two items for agent B, both the same, 1/3, and the capacity bound is 1. So what can you do? Pareto efficient solutions are only 3. Either you give everything to A by assigning A this big item, or you have a sort of balancing with 1/2, 1/3, or you give items only to B. The system optimal solution would be the first one, give everything to A. Clearly, the second solution seems to be more fair. Each agent gets at least a little bit, but it utilizes only 5/6 of the capacity. So how much capacity is wasted by fairness? And can you really measure fairness? Well, let's talk a bit about fairness. The classical way is this maximin fairness. So you want to make also the least happy person as happy as possible. So you maximize the minimum allocation over all agents. That works fine, but only if the agent if the items are somehow scaled in the same way. So maybe the two agents or the subsets of the two agents live in a bit different worlds and have very different items to compare. So a different point of view would be a normalized maximin fairness. It's also called Kalai Smorodinski fairness, where we look for each agent. What could he do on his own? So what is the optimal utility that an agent would get acting on its own? So that is U star, the best egoistic solution for one agent. And the same for agent B. And now we say that you want to get at least a certain proportion of this hypothetical optimum. So you say that the fair solution divided by the best possible individual solution. So it's a percentage of the egoistic solution that you get. And you want to maximize the minimum share of your individual independent solution. Of course, if the item sets are the same, then also the utilities are the same, and this normalized maximin coincides with general maximin. We will use a third fairness concept. It's called proportional fairness. Maybe it's better to look at this text. A solution is proportional fair if any other solution, which is maybe better for one person, let's say for agent A, so it gives a relative improvement for agent A, so let's say 5% better, but then the loss inflicted to the other agent is smaller than 5%. So it's some sort of Pareto efficiency, but in a relative sense instead of an absolute sense. So you say that, can you give one guy 10% more if the other loses its own valuation only 3%? And if there's a solution that cannot be improved anymore for any of the agents, then we say that this is a proportional fair solution. Such a solution is always Pareto efficient, but unfortunately it does not always exist. So we have to consider if this even exists. As we had in this tiny example before, where we utilize only 5/6 of the best possible solution, it's the general question, what do we lose if we go for a fair allocation instead of a system optimal allocation? So what is this difference? How much are we willing to sacrifice just for fairness sake? And this is the price of fairness that we pay. So it's the difference, so that's the loss of utility divided by the best possible utility. So if this value, price of fairness, how large can it be? In the worst case, it tends to 1. If a fair solution is almost nothing, then the price of fairness would be 1. In the best case, the fair solution is almost as good as the system solution, and this nominator tends to 0, so the price of fairness tends to 0, so we lose almost nothing. Well, does it make sense to study this price of fairness? Unfortunately, even a very simple example like this shows that you can always be as bad as possible. So you have one super large item and all the other items are epsilon. So of course the system optimal solution would be give this 1 to agent A and that's it. What is a maximin fair allocation? Well, you have to give B something, so at least epsilon, but then you can give A only epsilon as well. So you end up with this solution of epsilon and 2 epsilon. So the price of fairness goes to 1, which is the worst possible case. Well, that would close the story, but you should note that in this worst case example, you have this item of weight 1, which is a bit strange that an agent can utilize the full resource, the whole bounded capacity just with one item. It's a bit unnatural. So we could say that items are not so large. And that means we introduce an upper bound alpha on all the item values. And that's the same what is done in the bin packing literature. When you analyze the worst case performance of bin packing heuristics, you do that parametrically depending on an upper bound on the largest item weight. And that's what we want to do. So we look at the price of fairness, but depending on an upper bound alpha on the largest item for item weight, item value. Okay, so how far can we get with that? We can characterize exactly the price of fairness. So for maximin fair allocation, it's this a function in different intervals. So it looks roughly like that. So you have this constant part here in the middle between 1/2 and 2/3. You have an almost linear part from 0 to 1/2. These strange little things come from rounding the lower bound examples. You have to round up to the nearest integer in some sense, so they're not completely tight for every epsilon, but somehow asymptotically tight. And here you have this curve reaching up to 2, which is this function 2 minus 1/alpha. How do we get a strange result like that? So a piecewise function. Well, such a price of fairness obviously consists of a lower bound that follows from worst case instances, where you say that this is an instant that really gives a bad solution, and from upper bounds. And for the upper bounds, you have to know something, how bad can the maximin allocation be? And that means how good will the fair solution be under all circumstances. So construct a lower bound for a min-max fair solution. And that requires some analytical bounding, parametric in alpha, some case distinctions, and so on. For the lower, for the third part, for the third formula, where the price of fairness is less than equal alpha, it's a bit easier because you have an easy lower bound for the fair solution. Assume that the total fair contribution is less than the system optimum solution minus alpha. Then I could add any item, because every item has a weight less than alpha, to one or the other agent, and you improve the solution in any case. So either already all items were allocated, then the fair solution is optimum, or you can still add an item, but that means that the fair solution is not Pareto efficient. But we assume that we will restrict ourselves to Pareto efficient solutions, which doesn't hurt the fairness concept. So we know that this assumption doesn't hold. So our fair solution is at least the system solution minus epsilon, and there we are with this bound. Okay. Strange enough, for the normalized maximin fair allocation, exactly the same formulas hold, but the proofs are different. The lower bound examples are still the same, but the upper bounds are completely different because you need different arguments for this fractional expression. And that was quite complicated to do. That's all for separate item cases. Also considered proportional fairness, but I'll probably skip that. What about shared item sets? If there's one common pool of items from which you give to the two agents. There you can show that if such a proportional fair allocation exists, then it must be a complete equipartitioning, given exactly the same to both agents. And that's also a system optimal solution in this case. I will skip this proof, but in this case, also the other two fairness concepts coincide. So it's only interesting to look at maximin fairness for shared items. And for maximin fair allocations, we get again a piecewise function, this time a different shape, of course. It's also alpha up to 1/3, then it's constant with 1/3, and then it's a straight line up to 1. The proof is related to LPT scheduling, because you have the two agents and the items are like jobs, and you assign it to the agent like a machine with the lowest load so far. And so you can use similar techniques as in to machine scheduling. So summary of part 1, we could fully analyze the price of fairness for 3 fairness standard measures. We were only interested in this price of fairness. We didn't talk about how to find these fair solutions. All these problems are in p-hard, but only weakly in p-hard. We have done in programs with pseudo-polynomial 1 times. And some of the results can be generalized for more than 2 agents and also for utility functions with more general properties. Okay, so in the second part, I will introduce conflicts and I will move to more than 2 agents. It's based on a recent work with colleagues from the University of Koper in Slovenia and colleagues Joachim Schauer from my department. Again, we have items that should be distributed among several agents. But now the agent have a numerical valuation of the item. That was like the weight we had in the first part. Now it's some profit function. And again, we want a maximin fair allocation. So you have this profit function that gives a valuation to each item, but each agent has a different opinion. So it's like in the first part, you have shared items. It's one set of items from which the agent are given items. You have k, constant number of agents, and the profits can be very different. And you want to maximize the agent with the minimum satisfaction, so the minimum profit if you have additive profits over all items. This problem is known in literature as Santa Claus problem. So Santa Claus has n presents and wants to give them to k kids, and Santa Claus is a fair man. He wants to make the least happy kid as happy as possible. It was studied in literature. Probably the most well-known paper is by Bansal and Smorodinski. There are many variants where the profit functions are restricted to 2 values and some non-approximability results. So it was studied quite a lot. What we are doing in this part, we introduce a conflict graph. So if Santa Claus has a big sack of toys and maybe there are 2 remote controlled cars in his sack, my daughter wants only one of them, not 2 remote controlled cars. And my son wants to go on a skiing holiday with his school and he wants new equipment, but he can take either skis or snowboard, but he cannot take both things with him on his skiing trip. So that it's natural to have some distinction that only one of 2 presents makes sense. And so if the items correspond to vertices in the graph and the edges connect items that are in conflict that should not go to the same person, then we have a fair allocation problem under conflicts. Obviously, this conflict graph means that a feasible solution for one person must be an independent set for this agent. But that means now that we are probably not able to allocate all items. So instead of a partitioning problem, like in the standard Santa Claus problem, we can now only allocate a subset of the items. So another way of looking at the problem would be, we say we color the items with the color of the person or the number of the agent. And so we want to have a partial K coloring, where some items or some vertices are simply not colored, so they are left over and they cannot be added to any of the persons. Like in this triangle with 2 persons, 2 agents, clearly one item will not be allocated. Now, what is the situation we are facing? It's a tough one because the independent set problem that we have to solve for each kid is already a hard problem, as we all know. So the only way from a theoretical point of view is, can we look at special conflict graphs where we know that at least this independent set problem is polynomially solvable. So the first thing that comes to mind would be perfect graphs and one of the many subfamilies of perfect graphs where we have a chance to do something, because for problems where independent set is NP hard, cannot get any thing better than strong NP hardness again. So what are we looking for from the positive side? Well, the knapsack problem is already included here for 2 agents. If you have the profits of one agent is the objective function and the profits of the other agent is the constraint, the rate constraint. So it's even without conflicts, it's already weakly NP hard. So what we're looking for are pseudo-polynomial algorithms. And it will turn out that all our pseudo-polynomial algorithms permit also fully polynomial approximation schemes, so FPTAs. Whenever it's not strongly NP hard, we also get an FPTAs. So what type of results do we get here? So we have some negative results where we can say that a problem is still strongly NP hard for a certain conflict graph. Clearly, that only makes sense if the corresponding graph, if the independent set on this graph is polynomial. Otherwise, it's a trivial negative result. So negative result means the problem is polynomial solvable as an independent set problem, but it's hard as a fair allocation problem. Positive results, that would be a pseudo-polynomial algorithm and equivalent from that also an FPTAs. The most interesting negative results are bipartite graphs. So that's a fairly easy well-structured graph family. It's known that independent set is easy by a network flow, but it's strongly NP hard as a fair division problem under conflicts. So what we developed from this positive and negative results is the following map. Don't be shocked by this picture. On the upper side, at the top, you have perfect graphs. And then there are subfamilies of perfect graphs, comparability graphs and bipartite graphs. And if you show that bipartite graphs are already strongly NP hard for our problem, then all the way up, the graph families are also strongly NP hard. Here's this separation line between hard and easy. Easy is a bit strange because easy is still NP hard, but not strongly NP hard. So everything below the line could be solved with pseudo-polynomial algorithms. So this prominent class of chordal graphs, co-comparability graphs, biconvex bipartite graphs. I heard this morning there was a talk mentioning convex and biconvex bipartite graphs. So these are known. So here's the list again of the relevant positive results, except the bounded tree width, they are all perfect graphs. I will a bit talk about these biconvex bipartite graphs, mainly because I find them cute and they might be helpful for anyone who is working on something that is even hard on bipartite graphs. When we find positive results, we're always speaking about enumeration of profit combinations. So you have a tuple, an array with k slots, and in each slot you take you store the profit that you can generate for kit number 7, that is in the 7th slot of this array. And when a new item arrives, you can give it to one of the k persons. So for each tuple, you can get k new tuples. But of course, the difficult point is this part, how to add vertices and edges without violating feasibility of the previous tuples and without overlooking any tuple that could be generated. So this strategy sounds easy, just iteratively add items as long as they are not in conflict. But in general, it doesn't work because you will somehow fall into a trap by overlooking solutions or by producing infeasible solutions. So only if the graph has nice properties, you can proceed in this way. So what is a biconvex graph? Probably not known to all of you. It's a family where there is a bipartite graphs where there is a certain neighborhood structure. Neighborhood structure means if you look at this red vertex on the left side, you can arrange the vertices in both sets so that the neighbors on the right side, so the neighborhood, the adjacent vertices, are all in a consecutive interval. And that would be convex. Biconvex means that this property holds in both directions. So you have a blue vertex here on the right side, and its 3 neighbors are all consecutive. So this is the gadget to look for. All neighbors on the other side are in a consecutive interval. Whenever you have some matching problem where there's some time constraint, let's say that this job can be done between Monday and Friday, then you get naturally such a property involved if these are time dependent, so consecutive time intervals. That is, for instance, a situation where biconvex graphs may occur. For biconvex graphs, there's a nice structure theorem. I show you the picture. A biconvex graph can be arranged in such a way that you have on one side some upper vertices up to a vertex AL, and the lower part starting at a vertex AR. And if you look at this neighborhood between AL and AR, it contains all the vertices on the right side, and it's a bipartite permutation graph. And it's, if you look up graph classes, it's a co-comparability graph. And that's a graph that is easier to handle, for which we already had a pseudo-polynomial algorithm. Furthermore, these outlying vertices up there, they have a very special structure. Namely, they have nested neighborhoods. So the first graph A1 has these neighbors, and then the second graph in this, the second vertex in this order has a superset as a neighborhood, and so on. So these are completely structured. And that means if, let's say, A2 is given to some agent, then you know that A1 could be given to the same agent, because all items that are in conflict with A1 are necessarily also in conflict with A2 and in conflict with everything below. So you have a nested conflict structure, and that makes the enumeration of vertices easier. So as soon as you know what is the highest and lowest vertex to be given to one kid, you can then just assign whatever fits from everything above can be assigned without caring about conflicts. But how do we know what is the highest index for one agent? Well, you just guess it. You go through all possibilities. And for all these possibilities, how to handle this part at the top and at the bottom, you always solve the in-between part as a sub-procedure with a bipartite permutation graph. Okay, so we have n to the power of 2k guesses for these two outliers, and then this big sub-problem, and that's a pseudo-polynomial algorithm. So just as a sort of illustration how we deal with that. So summary in part 2, combining partitioning and independent set gives interesting new problems. I mean, that has been done for many other combinatorial optimization problems. Conflict graphs were done for bin packing problems, for scheduling problems. We did it for the napkin problem, and also for some graph optimization problems, conflict graphs were considered. And that's always interesting because it gives new questions from a theoretical point of view. We were able to draw up some partial complexity separation on the family of perfect graphs, and we have more or less finished an extension from biconvex to convex, where this ordered property holds only on one side. Okay, so I go to the third part. It's again allocating items to agents, but now it's, instead of maximin profit, we are now minimizing dissatisfaction. It's also based on joint work with the friends from Koper from Slovenia, with some other co-authors. So Andreas Dahlmann and Stefan Lendl from the Graz group, and a French postdoc in the Koper side, and the core team around Martin Milanic. The main topic is still the same, items to be given to agents. But now, instead of having weights or profit functions, now we consider preferences, not weights, not numerical values, but just the ordering. Say, I like A better than B. And we will assume that only some partial preference order is given, only partial information. So not a total ordering, but just some arbitrary partial informations. And again, we want a fair allocation. So this partial preference means that each agent has a directed graph, probably consisting of several components. And in the graph is directed, so it always points from a better liked item to a less liked item. And we want to allocate, again, items to agents, and each allocation implies a certain dissatisfaction value. I will explain that in more detail. Dissatisfaction will be items that I do not get, and I do not get any other items that I like better than this item. So I would really like to have this item. I would be happier if I get this item. Sort of, I envy the person who gets this item. I would like to have it. And now we want to minimize the maximum dissatisfaction over all agents. So let's go into more detail about this dissatisfaction, because it's a new concept that is something we introduced for these directed preference graphs, and it was not discussed before. If you have kids or grandkids or other relatives, you know the story about bringing presents to kids. If there are many presents, the kids would be overwhelmed to give profit valuations or to give us full total orders, or give them 10 presents and put them in a line. That would be hard to do for a small kid. But the kids will have certain ideas that are like this better than that, and this is even worse. I don't know about this too, but this is better than that. So it's possible for kids to express partial comparison. And what is for sure possible, that if I give a present to kid A, then kid B will know exactly if this makes him unhappy or not. So he might complain that I like this better. I like this better. What the other guy gets is better than the thing I have. And it doesn't help to give an additional present to the unhappy kid, which doesn't like so much. So you say, this is the trophy, the very attractive present, and this boy doesn't look at all the other presents because this is better than this. So he wants something at least as good as that. If he gets something like that, he will forget about these presents. But if he doesn't get them, he will be unhappy. And as a fair parent, we want to improve the happiness of the most unhappy kid. So back to graphs. If you have a directed arc from A to B, that means the agent prefers A over B. And of course, each agent has its own graph, its own preference relations. You can also say that a present dominates another present if, for a certain agent, if there's a path from U to V. So if U is better than some intermediate items and better than V. And the dissatisfaction, once again, as I already wrote it before, it's the number. We count the items that the agent does not get, and it's not dominated by a more preferred item. And we count the total number. And we can now minimize the maximum dissatisfaction. We could also minimize this total dissatisfaction, the sum of dissatisfaction. Could also make sense, but it's not really a fair concept anymore, but it was also in our study. There are other concepts of fair division, like it's always a bit difficult to capture preferences. You can always sort items, but you cannot sort allocations. I mean, there's one paper who said that the agent should rank all possible subsets of items. And we know there are 2 to the n possibilities of generating subsets, and it will be quite a hard task to rank all these 2 to the n subsets. More tractable, but a bit very rough approach would be to have dichotomous preferences, to say that the items are only partitioned into good and bad items. There are items that I like and items that I don't like. That's a bit weak, what you can really do with that. An extension of that would be that you have again these good and bad items, but there is a ranking between all good items and the ranking among all bad items. And this information is then included in the valuation of subsets. So let's look at an example. So this is a preference graph for one agent. So there are these isolated items 8 and 9, and there's this tree-like preference structure for the first 7 items. And now let's assume that agent I gets these 3 presents, 4, 6, and 9. What is the dissatisfaction? Dissatisfaction are items that the person liked to have but didn't get and is not compensated by something better. So that's A1, A2, A3, and A8. A8 is not dominated, maybe it's the top present. It's just not comparable to the others, but it's still something that I would like to get. Now, if I say, okay, to make this person more happy, I add present number 5. Nothing changes because I already get present number 4, and this is something I like better. So I don't sum up all presents. 4 is better than 5, so I don't care if I get 5 or not. But if I get 2 instead of 4, that would improve the situation. Because now I don't care about A3 anymore. I've got 2, that's better than 3. I only envy people who get item 1 and item 8. So my dissatisfaction is now only 2. So by moving one, so the allocation just from 1 item up, I change it from a dissatisfaction of 4 to 2. Instead of dissatisfaction, we could also speak of satisfaction. So this item 2 is better than 3, 4, 5. So it has a satisfaction value of 4. It's also a different way to talk about it. So if an item is covered by some item that I get, then it's dominated, it's a satisfaction of this item. And indeed, we can, instead of minimizing total dissatisfaction, we can maximize total satisfaction. But that works only for the sum case, not for the maximin case. In the maximin case, satisfaction and dissatisfaction cannot be exchanged. Easy to see in this small example. Agent 1 has 3 presents, and agent 2 and 3, they like only E or C. So what would be the maximin satisfaction? So you give 1 present to each person, so that each one gets a satisfaction of 1. What is the min-max dissatisfaction? To reduce dissatisfaction, you have to give 2 items to agent 1. Otherwise, his dissatisfaction is 2, and it will be the largest dissatisfaction. So to bring his dissatisfaction down to 1, you have to give to agent 1 2 items, and then probably nothing to one of the 2 agents. So it has also dissatisfaction 0. So the solution is quite different. So what could we do for this dissatisfaction story? Again, we derive complexity results for different graph classes, such as very simple structures, out stars. It's just a nice present and many uncomparable but less nice presents. Or out trees, as we had before, or direct matchings. So matching is an interesting case because it's so simple. It's just pairwise comparison of 2 items. So you have all these items are incomparable among each other, but there are some pairs that you can compare. So that's a directed matching. Or extending these matchings, you have maybe some paths, disjoint paths. Here's a summary of results. I don't want to bore you with the details, but I want to make you look at this case. So directed matching. For arbitrary k, it's MP complete for in the min-max case, and polynomial for the min-sum case. It's one of the few problems where there is a complexity difference between min-max and min-sum. If you restrict the situation to 2 agents, like we had in the first part, then also the min-max case is polynomial. And in the remaining minutes of my talk, I want to just point quickly what these matchings results, where they come from, especially the positive result. The directed matching means some dissatisfaction can be solved in polynomial time. To do that, we construct an auxiliary graph from this preference graph as follows. It's a sort of nice encoding of the instance. So for each item, you have a vertex Z. So Z5 for item 5 and so on. And then you express which agents are interested in this item J. And let's say agents 1, 2, and 4 are interested in this item. So I introduce vertices xj1, xj2, xj4, because these three guys, 1, 2, and 4, they would like to have present number Z, and you make a connection to them. And this is the same for present number R. And here you say person 1, 2, and 5 would like this present. Okay. And now you have to somehow encode the preference structure. Now the preference structure is matching, so it's very simple. So what if person 1 has a preference arc in this matching from J to R? Then we introduce a new vertex, YAI, saying that the arc A belongs to agent 1, and this arc connects items J and R, both the copy that is assigned to agent 1. Or for agent 2, he likes R better than J, so there's a connection between R and J for the copy of agent 2 goes to a new vertex symbolizing this arc B. Okay, and now what about the weight? We are going for a weighted matching. The weights count the number of undominated vertices. So on this auxiliary part, these are all very large weights L, and on the other side, you have a weight 1 if J is on the lower part of the matching, so it's not so well liked. So you get a 1 here because giving this to the person is a satisfaction value of 1. The other way around, if this is the beginning of the arc, so it's the better liked present, that means if this agent gets this item J, that would be a satisfaction of 2. So you make a 2 here because assigning this item to agent 1 would give him satisfaction 2. And now we just run a maximum weight matching on this auxiliary graph. Why does it work? Well, if there is only one of these edges can be in the matching, so that means each item is allocated at most once, so we are safe there. And on the L side, each vertex here corresponds to an arc, and that means that two items are compared. And so it makes sense to one agent to receive only one of the two, either the upper or the lower. But if you get the upper of the matching, you don't want the lower in addition. So that guarantees that you get only one of the two, and you will for sure assign them because they are like big L, and you count these satisfaction values. Okay. If we have that's the mean sum case, because you just sum these satisfaction values. If you have the min max case, then it's NP complete. Since we don't have numbers involved, everything is strongly NP complete. It's an exact cover by 3 sets. And finally, if we have only 2 agents, then we can still do it in polynomial time. How do we do that? Well, we look at these 2 preference graphs of the 2 agents, and we just put them on top of each other. We just merge them. And what is the merging of 2 matchings? It's a collection of paths and cycles. If there are 2 identical edges, then we count this as a cycle between 2, like 2 parallel edges are also a cycle. This is a very special structure. If this union of the graphs are just paths and cycles and they are alternating, and we now can enumerate these dissatisfaction profiles. So all pairs D1, D2, which correspond to an allocation where agent 1 has a dissatisfaction D1 and agent 2 has a dissatisfaction D2. In each path and each cycle, it's relatively easy to derive all these profiles. I mean, some details are required, but that works fine. And once we have done that, we just aggregate all these arrays into one by collecting one after the other and merging it to the already collected set of dissatisfaction profiles. Merging means you take a new possibility, a new profile, and add it to each of the existing profiles, and that gets you a new profile. Okay, so we introduced a new version of expressing happiness or dissatisfaction. We got surprisingly strong hardness results, so even for very simple graphs like these matchings, some of the problems are already strongly NP hard. We also worked a bit on fixed parameter tractability, and what we are currently finishing is the case where all agents have the same opinion. So if they share the preference graph, so if there's only one preference graph and they all have the same valuation, all the agents, then all the negative results have to be reconsidered and don't hold in the same way. So, summarizing all together, fairness gives rise to many interesting optimization problems, and there are quite different ways to express fairness. Fairness is now becoming, or has already been for some time, a very hot topic. Just think of sharing economy, sharing costs of common use of resources, and in many cases, finding fair solution is much harder than finding efficient optimal solution. And we should all continue to be fair to each other. Thank you.
Thank you. So any questions? Oh, Alexandra.
Hello, Ulrich. It was a very nice talk. And okay, I have one question. Okay, let me raise down my hand. In some of your examples, which were very meaningful, I have the impression concerning the last topic, the minimizing dissatisfaction. I have the impression that sometimes the optimal solution, the solution that minimizes maximum dissatisfaction, may not be Pareto optimal. So my question is, did you address also the problem of simply finding the set of just one Pareto optimal solution? Do you think are there implications of the results that you found on the problems on the complexity of finding Pareto optimal solutions?
Pareto, you mean if you count just the number of items given to one person?
Yeah, yes, the dissatisfaction index of each agent. Let's say, so if you improve the situation of one agent, you cannot improve one agent without making a damage to the other agents. That's it.
We didn't look at it from that perspective, but it may well be the case. I think that it's not Pareto.
Yeah. Yeah, I think in the very simple example that you gave, in which you had 3 items, this one. If you give A, B to agent 1, but still you can give C to agent 3, which does not change the value of the minimum dissatisfaction, but it becomes paradoxical, if I'm not wrong, if I understood it correctly. So, I mean, that might be another topic to address, to characterize the complexity and the number of optimal solutions.
Yeah, that's something that we should look at. Yeah, thank you.
Any other questions? Ulrich, I have a question. So this is about in your first part of your talk about fair allocation of indivisible items. Yeah. So now I understand in your approach, you treat these items as goods, so they bring positive utility. Yeah. Suppose we consider these items as chores. Okay, so it will bring costs instead of benefits, so it will decrease your utility. So will your nice picture change if that's the case?
So you mean the items cause some cost?
Yeah, you bring on negative utility instead of positive utility.
And then
still you want to be fair, but everything just reversed. But it seems not symmetric, these two things.
So you would minimize the maximum cost that you inflict on someone.
Right. Yeah, yeah.
That would change things because our results rely a lot on this bound. We have this capacity bound. At most, that much can be distributed, and you want to be as close as possible to this bound.
Of course, you can just, instead of upper bound, you just bring lower bound. So everyone will incur at least some cost. So as a lower bound instead of upper bound as capacity, then so I suspect that the picture
we have to assign at least items with a total cost that much, and then who is that would be different. So that would clearly change all the results, because it's like somehow a bit, I mean, in multiprocessor scheduling, you also have this min-max and max-min objectives sometimes, and that's not the same, and that would also apply here.
Yeah, thanks. Any other questions? Okay, if there's no question, before I can close our session, let me propose everybody just unmute their mic and just give our previous speaker a round of applause. All right? Thank you. And then the session is closed. See you tomorrow.